Okay, thanks. Welcome back to this plenary session, or this set of plenary sessions. I will briefly introduce our first speaker of the afternoon. I won't go too far because it would take most of our time. So Susan Athey is a professor of economics at the Graduate School of Business at Stanford University. She's a well-known economist, so again, I won't go much into all the topics she's been working on. She received the Bates-Clark Medal in 2007, so that for those who know, that should tell you already. So that's the highest prize for economists below 40 in the US. So that should be enough of a long introduction, and she will talk for about 40-45 minutes. If there are questions, she might eat into the question time after that. So we'll organize so that more or less you'll have time to ask questions during the talk if it's really related and important to what Susan is doing at the time, or keep them for the end, and we'll have a long question Q&A session at the end of the talk.
So first of all, thanks so much for having me here. This is such a terrific conference, wonderful presentations this morning, and a really great group of people. And it's just so exciting how this topic is attracting so much interest from so many smart people. So I want to talk today about some work that I've been doing, bringing together machine learning and econometrics. And this really, I came to this topic, I started working with Bing Ads in 2007. And at the time I came in, there were so all these machine learning people and engineers running the Bing Ads system. I was the only economist. And so at first I sort of thought that the way people were thinking about data was sort of quaint but misguided. And then after a while, I started realizing, after many arguments, that there was actually a lot that we could learn from what machine learning was doing. And certainly as I started to do my own empirical work, I found very quickly that my small data techniques were just completely inadequate for the job, not just because they couldn't handle data computationally, but also because they were very unsystematic. And so, most economists, when we work with a small data set, we only have maybe a couple hundred observations, 10 or 12 covariates, and so you spend a lot of time crafting your model and testing it. But when you go to settings with lots and lots of covariates and so on, you realize very quickly that you need to be more systematic about how you do model selection, and how you really you're really lying to yourself if you think that you, as a human or as an economist, have some insight about how all of these different attributes of, say, advertisers or users really would affect their behavior. And so I realized this big shortcoming in economics of being non-systematic. But then also, what really stuck out from the machine learning side was the lack of a framework for causal inference, and in some sense, just very little attention to anything outside of prediction. And so it made me realize, especially, of course, there's exceptions and there's parts of machine learning that focus on causal inference, but that you could have lots of people with PhDs who didn't even have a language for speaking about it. And what that turned into for me was really an agenda. At first, I went out and started talking about this and sort of complaining about it and suggesting other people work on it. And finally, I just started working on it myself. Hopefully, though, not to think that I'll have the last word, but to really partly illustrate, maybe to both communities, how much fruit there is in bringing together systematic big data methods with a framework for causal inference. And so the work I'll talk about today is just really a first step in that direction, but hopefully it will be provoking in thinking about what can be done. And so the specific work today is also motivated by another huge trend that's critical to all tech firms, which is A/B testing. And so we know that all the innovations that happen at Google and Facebook and Amazon and Bing and so on go through an A/B testing platform and randomized controlled experiments, and that's really the engine of innovation. And it's how these firms are able to innovate so quickly because they can really decentralize the innovation process. Anybody can have an idea and test it, and if the metrics look good, then you can ship that to users. You know, at Facebook, like an intern can change the code of what it is that you see on your screen, and the way that that's possible without the system breaking every day is through A/B testing. So I'll be talking about some techniques that I think can be used, and actually a bunch of the large firms are already looking at adopting these very techniques in terms of how they do A/B testing. In other work, I've actually pushed harder on the limitations of A/B testing. So if anyone's interested in that, I love to talk about that subject as well, but not today. So, you know, big data generally is very powerful. We can do personalization, targeted ads, customized offers, personalized search results, and personalized medicine. Generally, bigger is better, more data, better personalization. We're also doing all of this A/B testing, but what's kind of interesting is that there's a dichotomy between like the sophistication of the models that are used to do personalization and the ways that we evaluate them. So you can have a really complicated model that tells you what you see on your Facebook feed or what you see in Google search results. But then if you go and sort of test and if an engineer has a new improvement to that they want to test, generally you put it through the A/B testing platform and you see sort of, you know, 5 numbers. I mean, there's a bunch of numbers under it too, but you're going to say, okay, what happened to revenue? What happened to your favorite measure of user engagement and so on? You look at those aggregate numbers, you look at a t-statistic, you see if the results are statistically significant, and if they look good, you ship the algorithm. So you're going to do a new way of personalization. So the personalization algorithm itself is quite complex, but it's tested in this very simple way. And then, of course, if you say no, if it doesn't do a good job, then the engineers go back and tweak it and try to ship it again. Now, this can be a very cumbersome process, and the engineers might have to go back and understand, well, why didn't my algorithm work? What was the problem? And that can be a non-systematic search process. And so one of the things that we'd like to be able to do is say, anytime you actually test out a very complex algorithm where the people who built it themselves may not even fully understand it and how it works and why it works, to actually get some insight about where it worked well and where it didn't. And so that would be an example of trying to find heterogeneous treatment effects. The treatment would be changing existing algorithm to the new algorithm. The heterogeneous treatment effects would be saying, well, where does it work well? Does it work well for highly monetizing queries? Does it work well for certain types of problems, or, you know, so on? Okay. So, you know, when we think about heterogeneous treatment effects, there's actually sort of 2 kind of subcategories that are relevant, and actually the statistics of them are a little bit different, although today I'm going to focus mostly on the first one, estimating the impact of a treatment. Either an A/B test or an observational study of the impact of a system change or a marketing campaign, advertising effectiveness, or say a clinical trial for the effect of a drug. And so when we're doing that, what we're trying to do is systematically identify subpopulations, estimate treatment effects, and conduct inference. And of course, this might give us insight about mechanisms as well. If you find out this drug doesn't work for old people, then that might tell us also something about how the drug works, or give us ideas about how to improve in the future. Optimal policies, of course, you need to understand heterogeneous treatment effects to understand who to give what to. Estimating an optimal policy is trying to find the best function that's going to map from a user's characteristics to the ad that they see, or to the search results that they see, or so on. And another application might be computer-assisted medicine. The doctor in their office has a computer. They type in all of your attributes, and it's going to tell the doctor what the best treatment is. So that's like an individual setting. So the doctor has a computer, there's a black box computer, and they're going to spit back a recommendation. We could also, in some contexts, want to have optimal policies that are customized to subpopulations, but not individuals. Okay? And that seems like a subtle distinction, but I'm going to show you 2 different methods that have strengths and weaknesses for those. So if you think about the subpopulations, there might be cases where we don't really want to, for a variety of reasons, customize at such a fine-grained level. We might want to say that, this algorithm triggers for commercial queries, or this algorithm triggers only for queries that are classified to be good reference queries or something. So we might only ship an algorithm when certain conditions are met. We might want to have a poster on the doctor's wall instead of a computer that tells them what the guidelines are. A government might be assigning eligibility for programs, and they need to have transparency. So you need to have a little tree diagram that you can post on your website so people can see who's eligible for the treatment or not. Or a decision tree for salespeople. So when you need interpretability and simplicity, subpopulations can be important. If the FDA was going to approve a drug, they're not going to sort of approve a drug plus the computer-aided program, at least they haven't done that yet, but they might approve a drug for certain symptom categories. Okay? So now, motivated by these two questions, the subpopulation versus individual, both of which I'm going to address, we can think about a model for causal inference. And so, of course, I think much of this audience, I should actually ask, so how many people here from sort of social science and economics? So pretty large share, okay. But we do have some people here from more machine learning background as well, right? Some? All right, very good. So for causal questions, we want to know what would happen if a policy maker changes a policy. If they administer a drug, change the minimum wage law, et cetera. And so one of the things I really want to emphasize is that it's going to be a huge difference between the standard supervised machine learning paradigm and the way that we're going to think about causal inference is what Holland called the fundamental problem of causal inference. We don't see the same units at the same time with the same counterfactual policy. So I could give half of you coffee, half of you not coffee. I could take your temperature afterwards. But for none of you do I actually see at your individual level the treatment effect of coffee. I could calculate the average by comparing one half of the room to the other, but I don't see it for any individual. And so why is that so important? Well, the whole kind of paradigm of supervised learning is that you don't care about statistical inference. You don't even think about it because you have this approach to how you evaluate models. And that is that you have a test sample, you hold out 10% of your sample, and you see how well your model does at predicting that 10%. And so that's the gold standard. It doesn't require any assumptions. You know, if your model is a good model, it's going to predict well in that 10% holdout sample. You're going to look at the mean squared error. If you do well predicting, it's a good model. If you do badly predicting, it's not a good model. And you don't need to think about assumptions or asymptotic properties or anything else. In the world of causal inference, that is explicitly not the case. We don't know what the ground truth is for anybody. And of course, we know in the economics problems that we study, like the near and dear to our heart, like demand estimation, in general, if you regress quantity on price, you get a positive slope. So you take a typical data set with quantity and price in it, and you'll see price goes up, quantity goes up. Why do you see that? Well, it's because people generally raise prices in times when people are willing to pay more, and they're seeing high demand. And so, of course, the best predictive model would say, yes, higher price, higher quantity. If you had a 10% holdout test set, to predict that test set, you would put a positive coefficient on price, but yet, of course, you would never tell a firm, raise your price to get more sales. Okay? So we know in economics that predicting in a 10% holdout sample is very different from getting causal effects. We don't want the best predictive model, but that's not generally the paradigm for supervised machine learning. So I'm going to use the potential outcomes notation in this talk. It's a Rubin causal model. So we say yi of w is the outcome a unit would get if they were assigned a treatment w. So yi of 1 is what your temperature would have been if you had gotten coffee. Yi of 0 is what your temperature would have been if you hadn't gotten coffee. And your individual treatment effect is the difference between those potential outcomes. Of course, if you're coming from an industrial organization perspective, we could think of this as like a demand curve, and you might have a hypothetical amount you would buy at different levels of price. Okay? And so the causal question is then, what would happen if you changed that W? And if we, of course, in the case of heterogeneous treatment effects from just like online big data settings, we have lots and lots of attributes of individuals. So instead of thinking about just an overall average treatment effect, which is what the small data economics people have usually focused on, we might want to get the conditional average treatment effect, which is your average treatment effect conditional on your characteristics. If I wanted to get a personalized prediction, that would be my goal. For every person, I want to know, for given all of your attributes, what's your expected treatment effect. So, of course, in an economics audience, this slide is going to feel a little funny, but actually in statistics even, sometimes you have to argue about this, and certainly in machine learning you have to argue about this. The importance of inference. By inference, I mean like hypothesis testing, knowing the asymptotic properties of your estimators, knowing how you would get statistical significance. Now, in an A/B testing platform, statistical significance is very important. If your result is not statistically significant, then your algorithm may not get shipped. So in some sense, people recognize that. But in the general prediction literature, and I'm working with a statistics PhD student, he's gotten lots of negative feedback about looking at questions of inference. So so maybe you intrinsically care about this. You can't publish an economics paper if you don't have some sort of confidence interval around your estimates. But why would you care separately of getting your papers published? Well, in terms of thinking about how you evaluate a model, I just mentioned that supervised machine learning models have this nice tradition that you evaluate the model by its performance in a test set. The mean squared error of your model on a test set is a gold standard of supervised learning models. But for causal effects, we don't observe the ground truth. I'll show you some techniques we have for estimating it to try to substitute for the way things are normally done in supervised machine learning. But statistical theory is going to play a much more important role in evaluating your models because you don't have that ground truth available to you. And so related to this, it's important, it's actually issues of inference that have really slowed down the application of systematic techniques to studying heterogeneous treatment effects. So in particular in medicine, like the FDA kind of bans you from data mining. And this is the bad version of data mining. That is, I ran a randomized experiment. My average effect was 0, at least not statistically significantly different than 0. But I look in my data and I find, aha, men between 62 and 65 that had the following 3 pre-existing conditions. The drug worked great for them. Please, FDA, approve that. That is explicitly not allowed by policy, okay? You have to specify in advance the heterogeneity that you're going to study before you do your drug trial. And if you discover later you could save a bunch of lives, too bad. Not allowed to be approved under that basis. You have to run a brand new clinical trial specifying that hypothesis in advance. Obviously, to people who do big data analytics, this sounds horribly inefficient because we think, my gosh, we could save lives by just looking at data. But the concern, of course, is that these findings might be spurious, and if you hunt hard enough, you'll always find some group. Similarly, in economic field experiments, there have been calls for pre-analysis plans, and a lot of leading scholars have pushed for those kinds of protocols, that you cannot report later a result that you didn't specify in exams. Now, to me, working with online data, this is horrible, because how would I possibly know? I don't have a theory about 1,000 covariates and their interactions. Completely crazy that I would, but of course we've got to be sensitive to this crisis in science. And I should say that there's been all sorts of news articles about the lack of replicability of studies and so on. So even in the small data setting, we were already fishing for results, but it's going to be easier to fish in big data settings. So the goal of this research then is to solve that problem. We want to allow the researcher to specify a set of covariates, have a systematic data-driven search for heterogeneity of causal effects, and at the end of it, I want to get valid confidence intervals that are meaningful. And that's what we're going to do. So I'm going to preview, and it's actually a little confusing, this subpopulation versus individual effects. So I'll take a few minutes to sort of preview our 2 results, and hopefully even just that will be a little thought-provoking for you. So our first paper identifies subpopulations. We find it in medicine it's called subgroup analysis. So instead of having subgroup analysis be, I specify in advance, I'm going to cut this by men and women and young and old, we're going to derive for you from the data the ways to split the data. The key elements of this is we're going to customize the way that these are normally done in machine learning, which is called regression trees, for the problem of causal inference. And then we're going to do something that isn't normally done in the machine learning literature, which is we're going to build what we call honest trees. They're going to be honest because they're going to use some data to decide how to develop the subgroups and other data to form the estimates. Now, if you were in a world where you're living with 500 observations and somebody told you to cut your sample in half, you would be very alarmed. You know, go to 250 observations, I couldn't show anything. And of course, I probably picked the most ambitious hypothesis I could get for 500 observations, and so I need all 500 of them. But if you're in a big data setting, you know, you would much rather learn a few things accurately. You know, having enough data isn't the problem. The problem is, have I actually really accurately discovered something? And so splitting the data isn't such a big deal. But there is a cost to it, and there's actually some current work in the statistics department at Stanford trying to figure out, you know, how to do better than splitting in adaptive models, but it's still pretty early stages from a practical perspective. Now, the advantage of these honest trees is it's actually very easy to explain to people why they work, because I can say, you know, I'm splitting my sample. So basically, I've got one set of data that tells me how to do my subpopulations. After that, it's as if God gave you those subgroups, and you can do the standard analysis. You can analyze that data any old way you want. And it's very clear, you know, that there's nothing going on behind the scenes that's fishy. So a key thing to note about this, the algorithm is both going to select the estimand and provide estimates and confidence intervals. And that's kind of a weird thing, that usually we say there's something we want to estimate, like tau of x, and we want to estimate tau of x really accurately. But this is not exactly what we're doing here. We're going to first decide that we want to estimate tau of x for 6 different subgroups, and then estimate them. So this is useful because the output is immediately interpretable. For some questions, the goal is to find subgroups. In other cases, the data may be too sparse to do personalized prediction. So I'm going to show you how I can improve on existing methods to do personalized predictions. But it turns out that if I have you guys in the room and I've got 1,000 covariates, there ain't no method on Earth that's going to give me valid confidence intervals for all of you without putting some more structure on the problem. There's just not enough data. And whereas this method of subpopulation is going to say, you could have 1,000 observations and 1,000 covariates, and I'm going to come up with 4 subpopulations for you. Can't guarantee they're the best subpopulations. I can't, you know, it's not, but what I tell you about those subpopulations will be true. And the confidence intervals will be accurate, because if I have, you know, 100 observations in a group, I understand exactly what it means to calculate a treatment effect with 100 observations. The weaknesses of this method is that when you do this subgroup analysis, they're really unstable. So if you take out a few observations and run it again, you might get different subgroups. And so that's another form of kind of data mining or fishing that we would have to worry about. And also, when you have subgroups, of course, you're not going to get the best fit for any particular individual. Somebody whose age is near the cutoff is going to have a treatment effect that's different from the average. So you're explicitly not getting the best possible prediction for everybody. On the other hand, fully personalized treatment effects, here we're going to do something that's based on random forest, and the trees in this forest are going to be honest causal trees. And so there the main theoretical result is going to be a consistency and asymptotic normality result. Now here it's actually, was kind of amazing to me. It took me like a month or 2 of digging to convince myself it was true. Random forest is an incredibly widely used machine learning technique. You know, hundreds of thousands of papers using this technique. I think, how is it that nobody knows if the predictions are asymptotically normal? How could that be? You know, why didn't anybody care? Didn't some graduate student somewhere answer this question? And the answer was basically no. A few people very recently proved consistency results under various conditions, but actually they were bias dominated, and so you couldn't actually get asymptotic normality. And so there's a couple problems. First, random forests are very complicated objects, and second, they're generally bias dominated. And as you get more and more data, the bias goes down and the variance goes down, but they're just always biased. And so the honesty that we introduce really helps with the bias. And that's partly how we get the results. You might ask, well, so what's the answer? Why did nobody care about asymptotic normality? Well, I just told you, the gold standard was mean squared error. Why would you care if some asymptotically you're normal when I know in my sample I have good mean squared error? Asymptotic normality just seems kind of boring. Like, who cares? And in fact, when the student first started working on this, some of the advisors were like, who cares? But actually, if you want to apply in social sciences, people care a lot, like as in you can't publish your paper without a confidence interval. So it's sort of table stakes for a method to have asymptotic normality. So personalized predictions are important for personalized predictions if you want to get the exact best prediction for every individual. and it allows you to fully describe comparative statics. The results will be much more stable, and so on. One problem with it, though, it's kind of a black box. Like I tell you, here's a computer, you put in your covariates, I can spit out a number, but it's actually even hard to describe your output. So I'll show you later some pictures, but these are sort of black boxy type of algorithms. And then the other weaknesses are, as I mentioned before, you're not going to have good coverage of your confidence intervals in areas where the data is sparse, and you do need a lot of data per covariate. Okay. So now let me go into a little more details on the subgroup analysis. So this is work with Hito Imbens. So first I'm just going to, since a lot of you from economics, I'll define for you what a regression tree is. So essentially, if you have outcomes y, attributes x, and some support, training sample with a bunch of independent observations, you can predict outcomes by building a tree. So I'm going to partition the covariate space into leaves, and it's recursive partitioning, so it comes out as a tree. And then within each region, I predict my outcome in a very simple way. It's just the mean. Okay? So just to see what this looks like this is an example of what a tree would look like. So you would split the tree according to covariates x1 and x2, and at the bottom, you're going to have average value of y, and say the proportion of the covariates in each leaf. And so a partition would look something like this. You know, in this region here, there's a lot of reds. In this region here, there's a lot of blues. And so what the algorithm does is it finds regions where things are similar. Okay. And so just to kind of think about how this relates to what we would normally do in economics, so it's like some of my previous published papers from my small data days, like I had timber auction data. And so I divided the volume of the timber tracts into deciles, and then I put dummy variables for deciles in the regression, and that was essentially taking out the average bid by each decile. Of course, if you have a couple covariates and you do decile by decile by decile, suddenly you have to estimate 1,000 parameters, when in fact, a lot of those distinctions weren't really relevant. So this is going to be a much more efficient way to do that kind of non-parametric stuff that we often did in econometrics already. But it's very familiar. In the end, once you know what these partitions are, you could get the predictions by running regression of y on a dummy variable for which region you were in, and you would get out of that the predicted values in each region. Okay. So just to kind of fix ideas, the red things are the things I'm going to change. The way these model works, there's an estimator in each leaf, which is a sample mean. When you try to actually decide where to split, you look at the mean squared error in sample, the difference between your predictions and the outcomes. And then you choose a penalty parameter, which penalizes the richness of the tree. And so you need that because you're looking at the data, you're snooping at the data to decide where to go, and of course, you're going to overfit. You're going to end up being biased because you're going to find the sets of things that just happen to have similar outcomes and put them together in a group. And so in order to control the bias, you have a regularization parameter, lambda, that penalizes the number of leaves, and you use cross-validation, that is a series of holdout samples where you take your model estimated on 90%, predicted on 10%, and see how well you do, and you find the regularization parameter that provides the best fit. So now I want to take this to causal inference. Again, this is the notation, and what we're trying to get now is tau of x, which is the expected treatment effect as a function conditional on the covariates. So how would you do this if you just went off the shelf? Okay, so if I just said, all right, I'm going to use machine learning and I want to take stuff off the shelf, and suppose I knew I wanted to do trees, although everything I'm going to say on this slide would apply to any other machine learning method as well. First of all, I could just take my treatment group and my control group and analyze them separately. I could fit a model on the coffee guys and fit a model on the non-coffee guys and take the difference. And a couple people have proposed this kind of technique, the few people interested in this intersection of machine learning and causality. A second approach is I could just throw all my covariates into one big black box. Like I could run a lasso or whatever I wanted to run on my W's and my X's and all their interactions. And then I have this big black box model, but then I could say, let me try to predict what that model would say the outcomes would be if everybody was treated. And then I take that same model and I predict what everybody's outcome would be if they were all control. I take that difference, and that's my estimate. And people have also tried to do that, but actually there's a bunch of papers doing this in the lasso context. So what is the problem with these? Well, in both cases, your estimation and your cross-validation are not optimized for your goal. they're trying to predict outcomes, not treatment effects. And so and one thing to know about machine learning models is they're going to use up all the degrees of freedom doing what you told it to do. So if you told it to predict the level of your outcome, it's going to work really hard to predict the level of your outcomes. But the things that affect the level of your outcomes might be very different than the things that affect your treatment effect. And generally, outcomes are highly predictable. Anybody who's worked with real data knows that it's very easy to find things that affect what your income is or your test scores, but it's very hard to find things that actually affect your treatment effect for a policy. So what we want to do is instead go directly after our goal of finding heterogeneous treatment effects in a world where we don't observe the ground truth. So I'm going to give you the first approach, and we're going to criticize this approach. So just to be clear up front, I don't like this approach. We reject this approach ultimately, but it gives you a sense of what's possible. So this approach is actually the approach I recommend, though, if you have 5 minutes to do things, because you can use this approach with literally 5 minutes. Okay, so what is it? How does this first approach work? I'm going to define a new variable, yi star I'll call it, and that variable is going to have as its average the treatment effect for every individual. So for Neil, just based on Neil, I'm going to get Neil's average treatment effect. Isn't that amazing? With no control. He's drinking coffee, I'm going to get his treatment effect. My estimate of his treatment effect is 2 times his temperature. And Steve over there, my estimate of his treatment effect, he didn't get coffee, is minus 2 times his temperature. It's a pretty darn noisy estimate of his treatment effect, but it's unbiased. Because if I average together Steve and Neil, I'm going to get, on average, the treatment effect. Here's the algebra here. If I do this doubling here in a 50-50 randomized trial, I take the expectation of this variable. Well, you're going to have 2. This is the 2. Half the time I'm going to draw a treated guy. Half the time I'm going to draw a control guy. I've got the minus sign in here. I gave a minus to Steve. And expectation, that's just the treatment effect. Very noisy, but that says at the individual level, I can actually construct an unbiased ground truth. Okay. So then, of course, if it's not 50-50, I divide by p, or 1 minus p. If it's an observational study, I divide by the propensity score. And by the way, everything today, I'm emphasizing the randomized experiment case, but everything, including the random forest stuff, extends to unconfoundedness cases. And actually, these methods are especially helpful for cases where you don't have a randomized experiment, because then controlling for covariates is super important. All right, so how would you change the estimator then in this case? Well, actually, the key thing about why this is so easy is you can write this line. Oops, you can write this line. Bleh. All right, you can write this line of code in R, or Stata unfortunately doesn't have trees built in, but you can write this line of code in R, and then you can run whatever machine learning algorithm you want. You can run lasso, you can run trees, forest, whatever, on this outcome, and then your algorithm is going to be going after the treatment effect. And so it's a very easy algorithm to do. What is it actually going to do? Well, in each leaf, it's going to take the sample mean of the transformed outcome as its predictor. It'll use mean squared error as its criterion. And that's because I'm not going to change any line of code at all except for the very first thing I do. What am I trying to predict? I'm predicting yi star instead of y. Now this actually has a bunch of stupid features that are actually pretty easy to fix. So the most obvious stupid feature is that if you think about within a leaf, what does it do? It's going to divide by your probability of being in that leaf. But actually this room is not quite balanced. So it would be like I pretended that this room was 50-50, and I divided by a half for all the people on this side and all the people on this side, but didn't account for the fact that you weren't 50-50. If you actually turned out to be 60-40, then of course you take the average of the 60% and you weight them appropriately. You take the average of the 40% and you weight them appropriately. So you have a difference between average treatment effects. But this estimator doesn't do that. It just makes a stupid mistake. So the first thing, which actually relies just changing a few lines of code, is that in the leaf, you would need to actually compute the average treatment effect instead of this kind of stupid biased version of the average. I mean, it's unbiased asymptotically, but in a particular sample, this kind of very noisy estimate of the average treatment effect. Second, we actually want to, this thing is a super high variance thing, so we can actually do better in every aspect of the algorithm. So we can do better in terms of how we split the leaves, and we can also do better in terms of how we do cross-validation. So one of the ways that we propose to do cross-validation is to use a matching estimator. So for every guy in the cross-validation sample, if Neil's treated, I'm going to match him up with Steve. They have lots of characteristics in common. I'll take their difference. That's my estimate of the ground truth. Now, this is actually going to go badly if I have like 1,000 covariates. So you're going to need to do some dimensionality reduction in that case for this to work well. And you'll see later how I propose to do that for the random forest case. OK. So what does this do then? Well, so what we call a causal tree is we're going to estimate the sample average treatment effect within each leaf. When we go to split, we're actually going to split by essentially the variance of the estimated treatment effect. It's a little non-obvious when you first look at it why that's the right thing to do, but essentially if you're in sample, you're going to estimate this average treatment effect in an unbiased way. So conditional on being unbiased, a more informative split is one that has more different predictions among the outcomes. If you weren't unbiased, this would be a crazy thing to do, but in sample, it's kind of analogous to using a Gini coefficient for those of you who know machine learning. And then out of sample, I'm going to use a matching estimator. So generally, there's not going to be one method that does well all the time. So the single tree or two tree approaches will be more similar to the causal approaches if things that affect the levels of outcomes also affect the treatment effects. But, and they're going to have, the two-tree approach has certain specific circumstances, like if the control outcome doesn't depend on covariates, then estimating separately is helpful. But generally, the methods we propose do better. Now let's talk about inference. The conventional wisdom is that trees are bad for inference because you have these discontinuous leaves. But actually, we don't care about doing inference about the tree structure. We want to do inference within the leaf. And then it's like super easy because I can separate out the tree construction from the treatment effect estimation. And then trees are really attractive because they give you something really easy to understand. So then, basically, like there is no theorem and proof about this. It's just obvious once you think about it that when you do this sample splitting, any valid method for treatment effect estimation and computing standard errors works on the part of the sample that was not used to construct the leaves. So it turns out actually that so far we mimicked the standard literature for adapting causal effect estimation, but honest estimation actually eliminates bias. So some of the fact that we're going to use this holdout, this half the sample to do our estimation. So we're doing further work to modify the criteria to actually account for the fact that we're going to do honest estimation later. And that's something that hasn't come up in the machine learning literature so far, but it leads to different splitting and cross-validation criteria. Let me show you briefly an application of this. So we did an experiment in search where I flipped the results, the first and third position, first and fifth position, first and 10th position, to see what the causal effect was of position. This was actually done for the European Commission, who was interested in, after Google admitted that they were putting Google Finance above Yahoo Finance and so on, what was the effect of that? Did that actually have any effect? And it had a big effect. You lose half your clicks going from position 1 to position 3. But we think these effects would be highly heterogeneous. And so by running a causal tree on this data, what I'm able to do is to look at which subpopulations of queries have a large average treatment effect, that's the ATE, and which ones have a small one. So we can see here there's a group that has a larger than average treatment effect, so the average was negative 0.135. These were ones that were classified to be reference queries. While over here we got about a 0 average effect for queries that were classified high on image and celebrity. So if you're looking for a celebrity, you're not really looking for information, and so it didn't really matter how you ranked the queries. And this is sort of what the rest of the tree looks like. One of the things that we wanted to look at was how much of a difference does it make to be honest versus dishonest? That is, to use the same data to choose your groups and to estimate effects as it does to separate them. And so here we had a couple 100,000 observations, and we've only got 20-odd groups. So you might think that by hundreds or thousands of observations per group, there couldn't be any bias left. But it turns out there is, because we worked really hard. The machine thought really hard about what were the best subgroups. And so they still get bias. And so the average effect, the average variance in the training sample of not being honest, as we call it, you get a 2.5 times higher variance than in the training sample. So we definitely have bias from not being honest. So let me actually, I'm running a little short on time, so let me skip. I want to tell you a little bit about the personalized predictions. So for personalized predictions, I'm sorry, and this is, we call them comparison forests. So in the prediction literature, people don't like trees for prediction because of these discontinuities. So generally what's much more popular from a pure prediction perspective is random forests. So in random forests, you build like 1,000 or 2,000 trees and you average them up. And you get different trees by bagging or subsampling the data and also introducing some randomization in how you split. So we developed these, we actually called them comparison forests or causal forests. What we use subsampling, but then in each subsample, we're actually going to do a causal tree. So we're actually going to take 2 subsamples, one to estimate the structure of the tree, the second to estimate effects. And actually the splitting is much less problematic here because you're already taking small subsamples. So now I'm going to take 2 small subsamples, but you're not losing anything. And so actually each tree is going to use different on a subsample. So you're going to use all of your data in constructing this forest. So there's actually really no loss from being honest, where at least in the tree case, you're losing half your sample, so you're losing some N. Here you're really not losing anything. You're just getting less bias. So it's really a great way to do this, I think. The output is going to be personalized predictions. So what is the way that you would normally do this if you wanted standard errors? Well, kernels and k-nearest neighbor estimators are the main things that actually have asymptotic properties in this type of setting. And what you can think of what the forest is doing is it's an adaptive nearest neighbor algorithm. If you've got 1,000 covariates and you try to be nearest neighbor in all 1,000 dimensions, you're going to be really far away in everything. So of course what you want to do is find the dimensions where it's important to be close. The reason nobody did this before was because it creates bias. And so they couldn't do asymptotic theory in that case, and the asymptotic theory might be false, like you might not get asymptotic normality. But our honesty helps solve that problem as well as some of the other detailed choices that we make. And so then we're able to do adaptive nearest neighbors and find the dimensions on which being close is important. So this is just a comparison. This is the true effect, and the color is the average treatment effect. These are 2 dimensions of covariates. Our approach does pretty well. The k-nearest neighbor estimates you see gets very blurry because it's finding people that are far away in these dimensions because there's some other dimensions. There's 6 covariates. They're getting confused by the other 4 dimensions. Here's for us versus, so it turns out we're better in terms of bias and variance. We just fit better. If you go up to 20 covariates, you know, the nearest neighbor just goes to hell. But we still do reasonably well, although at some point you're going to have problems also, especially near the boundaries. So the theorem in the paper, and I'm not going to go through all the details on this, but you can see they're pretty on the slide. We show asymptotic normality as well as propose a computationally practical estimator of the variance. These are the conditions we need. And then here's an example with confidence intervals put in. And we have bad coverage of confidence intervals. The confidence intervals aren't on the true effects at the edges, but we get good coverage in the middle. And then, but just finally, like, how can I apply this? Well, there was this big social survey that was done. They did a randomized experiment to ask if people are spending too much on welfare versus framing it instead as assistance to the poor. So the treatment effect is what's the effect of reframing the question on how likely people are to say we spend too much. And so here's a way you can summarize the output of the random forest. We look at whether the respondent had less income, was more liberal or more conservative. And so we can see the treatment effects are highly heterogeneous, and it's also, there's sort of interaction effects between income and political party. And we end up getting strong treatment effect heterogeneity in terms of, you know, for liberals, like the reframing doesn't matter. They didn't think welfare was bad to start with, but if you were conservative, you don't like welfare, but maybe you don't want to be mean to poor people. And so you get this heterogeneous effect. So just to sum up then, we think these are systematic methods. In some sense, we're bringing together the most popular and established methods from machine learning for prediction, but making them operational for social scientists who want to test hypotheses. And I think it was really interesting for me to just see that there were these wide open unanswered questions there that the thousands of people who use these techniques never cared about. And that's, I think, encouraging for us if we want to, you know, push the frontier forward, that actually it may not be so hard to adapt the methods to the needs we have. But there are some fundamental issues, like it does matter that you don't observe the ground truth, and that can be a big impediment, and that's the main thing to overcome. So, questions?